Hello, very good morning to you. Welcome to Quantum Online Academy. Yeah. So, yesterday we discussed about the potential step introduction. I told you, I discussed the case number 1 when E is greater than the particle energy is greater than the height of the barrier. So, what is going to happen? We are discussing in the yesterday's class. So, once again we have to see what we discussed in the yesterday's class. You able to learn about that yesterday's class, a little bit you have to learn in the potential step. So, what is your potential step? Your potential step is like this structure, we call it as a potential step. Here two regions are there. This is the region 1. In this region 1 the wave function is psi 1. This is the region 2. In this region the wave function you have to take it as a psi 2 wave function you able to take. Clear? Psi 2 wave function. Now the barrier height is at x is equal to 0. How much height is there? That height is V naught. Now you have to define the potential. How you have to define the potential? V of x is equal to, wherever you go, infinite square well or potential step or potential barrier, whatever it may be, you have to define the potential first. So, what it is the potential? V of x is equal to 0 for x is less than 0. V of x is equal to V naught for x is greater than 0. This is the definition of the potential step or defining the potential step. Now here two cases are there. One energy particle, you have to take the energy particle. In the case number 1 you have to take, what is your case number 1? Your case number 1 is E is greater than, the energy of the particle is greater than, E is greater than, which one we have to write? E is greater than V naught. This is the case number 1, correct? E is greater than V naught. Now you have to see, this is the case number 2, which case you have to take it as a, the E is less than the E naught. What is the E? E is the energy of the particle through passing through the particular barrier. Now you have to take, how we have to draw here? E is greater than E naught. You able to take, this is the V naught height of the barrier. Now this one is the first region you have to take, this one is a second region you able to consider. Now this E is what E? That E you have to take, your E is going to take it as a, this E energy is so greater than the energy of that barrier. Similarly, if you have to consider here also, you able to consider here. So what you have to take? This is the barrier height or finite height at x is equal to 0. Now your E, what is your E? E is less than the, E is less than the particle height is less than this. So you able to write it is. So E is less than here. Now we discussed in yesterday, this is the region 1. Which one it is? The region 1. Here you have to discuss about the region 2. Now we discussed in this. So now some portion of part should we have to incident. So what is going to happen? The incident beam is A e to the power of I k1x. Some portion of part should be reflected back in this direction. That reflection wave is B e to the power of minus I k1x is there. Some portion of part should be transmitted. The transmitted beam is C e to the power of I k2x. We discussed in the yesterday's class at x is equal to 0 when E is greater than V naught. So we discussed the reflection coefficient R is equal to modulus of k1 minus k2 is divided by modulus of k1 plus k2 whole square. This is the reflection coefficient, and the transmission coefficient T is equal to 4 k1 k2 is divided by modulus of k1 plus k2 whole square. This is the transmission coefficient. Now you have to take the reflection coefficient plus transmission coefficient is equal to 1. Yesterday we discussed these things where K1 is one constant and K2 is one more constant is there. You have to define here. So, what is your K1? Your K1 is equal to K1 square is equal to 2me is divided by h cut square, and K2 square is equal to 2m into e minus v naught is divided by h cut square. This is your K2 value. Clear? Now, what is the example is, so when E is greater than V naught, neutrons trying to escape from the nucleons. Neutrons means, so neutrons trying to escape from the nucleon, that is the example when energy is greater than the barrier height or potential energy. Now, we need to discuss about the when E is less than V naught. When E is less than V naught, in the classical region you have to observe, this is the barrier height is very high. Barrier height is very high means classically that particle cannot penetrate through this barrier. But in quantum mechanically that there is a probability of the finding the particle in the region 2 is existing. So, therefore, the quantum mechanical phenomena we have to observe here. What is the example of this E is less than V naught? Conduction electrons escaping from the metal surface. Conducting electrons escaping from the metal surface. This is the example of this. This one also you have to take it as a example of this condition. Now, we have to discuss about the, in the previous class we are discussing E is greater than V naught. So, that is why I am giving the bullets of the E is greater than V naught. Now, we have to discuss in detail in E is less than V naught. How we have to discuss once, you have to see our case, our condition of the case is E is less than E naught. What is our condition? E is less than V naught we have to take. Now, what is our diagram? Our diagram is this is the potential step. So, the at x is equal to 0 is a boundary condition. What is the height of the barrier? V naught height is there. This region is, you have to take it as a region 1. This region you have to take it as a region 2. Your energy of the particle is incidenting E is less than E naught, V naught you have to write it is. Now, in the region 1 that wave function you have to take it as a psi 1. In the region 2 the wave function you have to consider as a psi 2 you have to consider. This is your diagram I have to draw. Clear? So, now here that propagation constant is K1. Here the propagation constant you have to take it as a K2. Now, we have to apply in the region 1, we need to apply what is the your potential you have to take. Your potential V of x is equal to 0 for V of x is equal to 0 for x is less than 0. V of x is equal to V naught for x is greater than 0. This is your potential, correct? So, already this is the condition for the potential step. Now, you have to take, you have to apply in the region 1 the Schrodinger wave equation you have to apply. Take the region 1, you have to write it is in region 1. You apply the Schrodinger wave equation. So, what is your Schrodinger wave equation once you have to see? So, Schrodinger wave equation you know that. So, Schrodinger wave equation you have to apply. So, what is the Schrodinger wave equation? For one dimensional you have to see here the Schrodinger wave equation you need to apply. So, dou square psi 1 is divided by dou x square, because the particle is moving along the x only one dimensional, that is why I have to take it as a one dimensional. Dou square psi 1 is divided by dou x square plus 2m into in the region 1 e minus 0 is divided by h cut square into psi 1, which is equal to 0, because here V naught is equal to what we have to write it is V naught is equal to 0, that is why I have to substitute it here. So, therefore, dou square psi 1 is divided by dou x square plus 2m e is divided by h cut square into psi 1 is equal to 0. Now, you have to take this condition. So, this condition you have this parameter you have to take it as a k1 square. So therefore your expression can become dou square psi 1 is divided by dou x square plus k1 square into psi 1 is equal to 0. What is your k1 square? This is very important. After some time we have to use where k1 square is equal to, where k1 square is equal to 2me is divided by h cut square. K1 square is equal to, what is your k1 square? 2me is divided by h cut square. Now we need to solve this expression. How we have to solve this expression? Dou square psi 1 is divided by dou x square plus k1 square into psi 1 is equal to 0. Now you have to take, so this is d square psi 1 plus k1 square psi 1 is equal to 0. This expression you have to write in terms of f of d into y is equal to 0. You have to write it is. So therefore what is going to happen? So d square plus k1 square into psi 1 is equal to 0. So therefore you have to take f of d is equal to 0. You have to write it is. So therefore d square plus k1 square is equal to 0. So d square is equal to minus k1 square. So d is equal to plus or minus I k1. So the how many roots are there? 2 roots are there. These 2 roots also complex roots. Therefore that solution psi 1 is equal to, how we able to write, e to the power of I k1 x plus b e to the power of minus I k1 x you able to get. So e to the power of I k1 x, so plus e to the power of minus I k1 x. Now you have to see in the region 1 you able to take, this is the potential. In the potential step at x is equal to 0. So what is the height of the potential? V naught height is there. In the region 1 you have to incident the particle with augment incident a e to the power of I k1 x. With a e to the power of I k1 x, this is the incident beam. Which beam it is? Incident beam. Some portion of part should be reflected back. So in this direction that portion of part should be reflected back. This is e to the power of minus I k1 x. So what is these shapes? So these two beams can act as a sinusoidal beam. Sinusoidal, which beams? These are sinusoidal wave functions. So these wave functions we have to take it as a sinusoidal wave functions in the region 1. In the region 1, so we will get the sinusoidal wave function psi 1 psi 1 is equal to a e to the power of k1 x plus b e to the power of minus k1 x. This wave function is, which wave function it is? Sinusoidal wave function. Sinusoidal wave function. The first term is indicated the incident beam, the second term is indicated the reflected beam. Sinusoidal wave function. Which wave function you have to take? Sinusoidal wave function you have to take. Now the similar procedure you have to follow in the region 2. You have to apply the Schrodinger wave equation. So what is going to happen? You have to see. In the region 2 you have to take it as a region 2. So in region 2 we have to apply the Schrodinger wave equation you have to take. So in the region 2 you able to take the Schrodinger wave equation. So what is your Schrodinger wave equation? You have to see. So in the region 2 your wave function is dou square psi 2 is divided by dou x square because it is one dimensional plus 2m into e minus v naught is divided by h cut square into psi 2 which is equal to 0. But you have to take here v naught is greater than e. V naught is greater than e because our condition is, what is our condition? E is less than v naught. Our condition is e is less than v naught. So that's why v naught is greater than e. Here according to this equation, so what is happen? E is greater, e minus v naught is there. That's why you have to rearrange this expression. How we are rearranging? Dou square psi 2 is divided by dou x square minus 2m into v naught minus e is divided by h cut square into psi 2 is equal to 0. So psi 2 is equal to 0. this entire term you have to take this term, you able to take it as a constant, that constant you have to take it as a k2 square you able to consider. So therefore, where k2 square is equal to, you have to get it dou square psi 2 is divided by dou x square minus k2 square into psi 2 is equal to 0, where k2 square is equal to how much you are getting, where k2 square is equal to 2m into v naught minus e is divided by h cut square, 2m into v naught minus e is divided by h cut square, that is your k2. Now you have to apply this one, you able to take it in terms of f of d into y is equal to 0. So the homogeneous differential equation you have to take. So d square psi 2 minus k2 square psi 2 is equal to 0. So therefore you have to take d square minus k2 square into psi 2 is equal to 0. So therefore d square minus k2 square is equal to 0. F of d is equal to 0 you have to take. So therefore d square is equal to plus k2 square, therefore d is equal to plus or minus k2. D is equal to what you are getting, plus or minus k2. So therefore that solution, how we have to write the solution, once you have to see psi 2 is equal to a is you have to take it as a c, another constant you able to take c e to the power of k2x plus d e to the power of minus k2x we have to write it. This is the equation we are going to get. But you have to see here, so the wave function how we are going to happen, you able to see, this is the potential step you have to take here. So v naught minus e, so in the region 2 I am observing, so e is always less than e naught, this is the region 1, here two waves are there, this is the region 2, you have to take it as a region 2. So when how we this equation can execute, you have to take it x is equal to 0 up to this is prolonged, at x is equal to infinite is there. Now you able to see at x tends to infinite, at x tends to infinite, psi of x we have to write it is psi of x is tends to 0. So then only that wave should be exist. At x tends to infinite, the psi of x tends to maybe become as a 0, because here there is no probability is there according to the classical mechanics. In quantum mechanics, the finding the probability in the region 2 is existing, that finding the probability in the region 2 we need to calculate. So where it will be happen, you have to see here. So when psi 2 of x tends to infinite is equal to, able to see c e to the power of k2 into infinite, so plus e to d e to the power of minus k2 into infinite. So this is going to become as a infinite, this is going to become as a 0. So that's why this term is a redundant term. Which term it is? Redundant. Redundant term. This term is not necessary term, this term is a redundant term. So therefore our equation will become, so what will happen, psi 2 is equal to, your expression is going to take it as a d e to the power of minus k2x. So what is this? This equation is existing, this wave function is existing, this wave function in which shape it is? Exponential shape. This wave function is a exponential wave function. In the region 2 we are getting which shape of the wave function we are getting. Now you have to see here how we able to draw that wave function. Here some portion of part should be incidented with a e to the power of I k1x, some portion of part should be reflected, that is b e to the power of minus I k1x, some portion of part should be transmitted. How it is transmitted? That transmitted beam is this is the transmitted beam. So this is exponential beam, this is d e to the power of minus k2x, this is the exponential form. This is a sinusoidal beam. So these two beams are sinusoidal, these two beams are sinusoidal wave functions. So the sinusoidal wave function, this wave function is exponential wave function. which a wave function exponentially decay. So, exponential wave function you are going to get it. Now, we need to apply the boundary condition. We have to get the two expressions we are getting. So, what are the expressions we are getting? Psi 1 is equal to one wave function we are getting a e to the power of I k1x plus b e to the power of minus I k1x, we are getting that value. The psi 2 is equal to d e to the power of minus k2x. So, these are the two expressions we are going to get. This is the equation number 1 you have to write it is. This one you able to take it as a equation number 2 you have to write. Now, you apply the boundary condition. What boundary conditions we apply? Here I told the two boundary conditions when I told the particle in one dimensional box. At x is equal to 0, the barrier height is V naught. So, you have to take it as a E is less than V naught, clear. So, this is a finite height boundary condition, finite height boundary condition, finite height boundary condition. So, this boundary condition we also call it as a continuous boundary condition. This boundary condition we call it as a continuous boundary condition, finite boundary condition or continuous boundary condition. What is the finite out boundary condition? Continuous boundary condition is equal to that condition 1 is equal to psi 1 is equal to, here wave function is psi 1, here wave function is psi 2. Psi 1 is equal to psi 2 at x is equal to 0. This is the boundary at x is equal to 0. So, what is the second boundary condition? Dou psi 1 by dou x is equal to dou psi 2 by dou x at x is equal to 0. This is the boundary condition for finite height boundary condition or continuous boundary condition. First, you have to apply the first boundary condition you have to apply. How you able to get the expressions you able to see? The first boundary condition you have to apply, you may get. So, what you have to get once you have to see the first boundary condition you have to apply. So, what is your first boundary condition you able to see? Psi 1 is equal to psi 2 at x is equal to 0. This is your first boundary condition, correct? Now, you have to apply. What is your psi 1? A e to the power of I k1 into 0 plus b e to the power of minus I plus k1 into 0, which is equal to d e to the power of minus k2 into 0. So, e to the power of 0, e to the power of 0, any power 0 is equal to 1. So, therefore, a plus b is equal to, we have to write it as d. This expression you able to take it as a equation number 3. According to the first boundary condition, you are going to get it this one. Now, you have to apply the second boundary condition. What is your second boundary condition? Dou psi 1 by dou x, dou psi 1 by dou x, dou psi 1 is divided by dou x, we have to write it is dou psi 1 is divided by dou x, which is equal to dou psi 2 is divided by dou x at x is equal to, what we have to write, at x is equal to 0. This is the second boundary condition. First, you have to differentiate a into e to the power of I k1 e to the power of minus I k1 into 0 minus b into e to the power of I k1 e to the power of so minus I k1 into 0. So, e to the power of minus I k1 into 0, which is equal to, we have to write it as minus d k2 into e to the power of minus k2 into 0. So, therefore, what we have to write, a I k1 minus b I k1, which is equal to minus d k2 you are going to get. So, a I k1, so b minus b I k1, which is going to take it as a minus d k2 you are going to get. So, based on that, what we have to write it is a I k1 minus b I k1, which is going to take it as a, so d minus d k2. So, therefore, I k1 you have to take that side, a minus b is equal to minus d is divided by, so k2 is divided by I k1 you have to write it is, k2 is divided by I k1 you have to take. So, therefore, you have to multiply with I and divided by with I. So, therefore, a minus b is equal to, able to take it as a I K2 is divided by K1 into D. We are getting, this is the equation number 4 you have to take. So, this is the equation number 4. Now, we need to solve the equation number 3 and 4. So, what is going to happen once you have to see, we need to solve the equation number 3 and 4. So, what is your equation number 3? So, your equation number 3 is A minus A plus B is equal to D. This is your equation number 3, correct? Your equation number 3 is equal to A plus B is equal to D. Your equation number 4, A minus B is equal to D into IK2 is divided by K1. IK2 is divided by K1. This is the equation number 4. First, you have to add these two expressions. So, what is you are going to get it? So, you add these two expressions you have to take here. So, you have to add. So, 2A is equal to, so 2A is equal to D, you have to take the common. 1 plus IK2 is divided by K1. So, which is equal to 2A is equal to, from this A you have to write it is A is equal to, we need to take it as a D by 2 into, you take the LCM, K1 plus I, K2 is divided by K1. So, this is going to happen here. From this we need to write it is D also you have to take, after some time I have to use the D. So, D value is equal to, so 2 K1 into A is divided by K1 plus IK2, K1 plus IK2. This is the D value. After some time I have to use, you have to utilize this one. So, not only that, now you have to take the 3 and 4 and you subtract it, what is going to happen. So, equation number 3 is A plus B is equal to D. This is the equation number 3. A minus B is equal to D IK2 is divided by K1. This is the equation number 4. Now, you have to subtract the equation, you are going to take it as A plus and minus it will come. So, this minus A plus A get cancelled, therefore, 2B is equal to D, you have to take the common, 1 minus IK2 is divided by K1. So, therefore, 2B is equal to, we have to write it as D into K1 minus IK2 is divided by K1. So, therefore, B is equal to how much we are going to get, D by 2 into K1 minus IK2 is divided by K1. This is the B value you are going to get it. So, now you know the A value and you know the B value. Now, we need to get it. So, what value we need to get? B by A we need to cut. So, therefore, B by A is equal to, your B is D by 2 into e to the power of K1 minus I K2 is divided by K1. So, is all divided by, so what we have to write, your A is equal to D by 2, K1 plus I K2 is divided by 2 K1. So, D by 2 into, we have to write it is K1 plus I K2 is divided by K1 we have to write. So, D by 2 get cancelled, the denominator terms also K1 get cancelled. So, therefore, B by A is equal to, B by A is equal to K1 minus IK2 is divided by K1 plus IK2 you are going to get. So, which is equal to, this is the B by A value. You have to remember this value, you have to take it as a B by A is equal to K1 minus K1, B by A is equal to K1 minus IK2 is divided by K1 plus IK2. Now, we need to calculate the reflection coefficient and refraction coefficient we need to calculate. Before going to the calculation of the reflection coefficient and refraction coefficient, we need to calculate the current density or incident flux we need to calculate. Incident flux density is equal to, what is the incident flux density? Incident flux density is equal to nothing but the current density Ji. So, that current density Ji is equal to velocity into amplitude of A whole square. So, what is the velocity? Yesterday we discussed that one, velocity is equal to, now you have to write it is K1 square is equal to 2 m E is divided by h cut square. So therefore 2m is divided by h cut square into E is equal to 1 by 2 m v square. This is the kinetic energy of the particle. So therefore m square v square is divided by h cut square, which is equal to what it is, k1 square is equal to, you have to remove the square on both sides. So therefore k1 is equal to m into v is divided by h cut. So therefore velocity is equal to h cut k1 is divided by m. So therefore what we have to write it is h cut k1 is divided by m into modulus of a square, which is equal to what is this? This is the incident flux you are getting. Similarly, you able to get the reflected flux density. What we have to going to get? The reflected flux density is equal to, what is your reflected flux density? J suffix r is equal to velocity into modulus of b square. So therefore similarly you have to get it, h cut k1 is divided by m into modulus of b square, you are going to get it. This is the incident flux and velocity of the reflected flux we are going to get. Now we need to calculate, so what we are going to calculate? The transmitted flux we are going to calculate. So what is your transmitted wave? Your transmitted wave is d e to the power of minus k2 into x. Now we need to calculate the transmitted flux, means transmitted current density we need to calculate. How we have to calculate the transmitted current density? Already we discussed h cut by m into the imaginary part of psi conjugate into gradient of psi. So this wave function is which wave function? It is a real wave function. So therefore the imaginary part of psi conjugate into gradient of psi is equal to how much you able to get? 0, because your psi 2 is what is your psi 2? Your psi 2 is a real wave function. There is no imaginary term in that wave function. So that's why that imaginary part is 0. So therefore that the transmitted flux density h cut by m into 0, is equal to 0. So therefore the transmitted flux density is equal to the transmitted flux density is equal to how much you are going to get it? That is the 0. You are going to get it as a 0. Now we need to calculate the reflection coefficient and transmitted coefficient we need to calculate. How we have to calculate the reflection coefficient? Once you have to see, our ultimate goal is we need to calculate the reflection coefficient. So what is the definition of the reflection coefficient? The definition of the reflection coefficient is R is equal to J reflected flux is divided by flux density is divided by incident flux density. What is the reflected flux density? H cut k1 by m into, so we have to take it as a modulus of b square. We have to write it is modulus of b square. So what is the incident flux density? H cut k1 by m into modulus of a square. This one get cancelled. Therefore the reflection flux density is equal to modulus of b by a whole square. You have to write it is. So already you know that b by a, r is equal to b by a is equal to k1 minus I k2 is divided by k1 plus I k2 whole square is there, modulus of whole square. So therefore what we have to write? You have to remove that modulus, you able to get it. So k1 square plus k2 square is divided by, here also k1 square plus k2 square. K1 square plus k2 square get cancelled, that is going to take it as a 1. This is the modulus. So therefore r is equal to 1. If r is equal to 1 means the reflection coefficient is 1. means the total wave is reflected back only. The total incident beam, the total incident wave, the total incident wave is reflected back only, reflected back only. The total incident wave is reflected back only. Now we need to calculate, so the total wave is reflected back only. We need to calculate the transmitted flux. You have to calculate. How we able to calculate the transmitted flux? Once you have to see the coefficient of transmission, the coefficient of transmission or transmission coefficient, you have to write it is transmission coefficient, transmission coefficient we need to take, transmission coefficient we need to write it is. So what is your transmission coefficient? Your transmission coefficient T is equal to the transmitted flux is divided by incident flux. Transmitted flux is divided by incident flux. So what is the transmitted flux density is equal to 0. The incident flux whatever it may be 0 by something is equal to 0. So therefore T is equal to 0 you are going to get. When E is less than E V naught, you are theoretically you are going to get it the transmitted flux is equal to 0, means no transmitted wave, no transmitted wave, that no transmitted wave is existing. So therefore R plus T is equal to how much we are getting? 1 plus 0 is equal to 1. This won't be change, R plus T it will become as a 1 you are going to get it. But we have to then, so therefore what we have to write it is there is no transmitted beam, means when E is less than, you have to write it is the theoretically when E is less than V naught, the particle energy is less than the barrier energy, the reflected beam is totally reflected. So the incident beam, which one we have to write it is the incident wave function, the incident wave function is totally, the incident wave function is totally reflected back, the incident wave function is totally reflected back. This is very, very important condition theoretically, but according to the quantum mechanics we need to give one note. So what is the note? Once you have to see, we need to calculate the wave function is existing in the region 2. So in the region 2 is wave function is existing. What is that wave function? D e to the power of minus k2x. This is the wave function where it is existing when x is greater than 0. In x is greater than 0. If wave function is existing, means there is a probability of the finding the particle in the region 2 also existing. So therefore that probability we need to calculate. So what is the probability? How we have to calculate the probability? Once you have to see, so 0 to x is equal to 0 to infinite, you able to take psi 2 conjugate of psi 2 into dx. Now you have to substitute here integral 0 to infinite psi 2 conjugate, it is a real function, psi 2 conjugate also you are going to get it as a d e to the power of minus k2x, psi 2 also you are going to get it as a d e to the power of minus k2x into dx. So therefore you have to take it as a d square into integral 0 to infinite e to the power of minus 2 k2x into dx. But you know one standard integration formula. So what is your standard integration formula? Integral 0 to infinite e to the power of minus ax into dx. E to the power of minus ax into dx is equal to 1 by a. This is your standard integration formula. Based on that standard integration formula, the probability is equal to how we have to write it is d square into e to the power of minus a into dx. So what is your e to the power of a? 1 by a, 1 by, so 2k2 I am writing, 1 by what is going to happen? 2k2, d square into 2k2. But your d value, no. So what is your d value? already I am giving the d value is equal to 2k1a. 2k1a is divided by modulus of, so k1a is divided by k1 plus ik2, this is the d value. Now you have to substitute there. So what you are going to get it once you have to see the probability of that particle, how we are going to get the probability in the region 2, probability in the region 2 is equal to d square is divided by 2k2. Your d is equal to, what is your d? So your d is equal to 2k1a, that is 4k1 square a square is divided by 4k1 square a square is divided 2k2 into, so k1 plus ik2 whole square, this is the value you are going to get. So this value is obviously is not equal to 0. So the probability of the finding the particle in the region 2 is not equal to 0. So therefore the probability of the finding the particle, what we have to write it is the probability of the finding the particle, the probability of the finding the particle in the region 2, the probability of the finding the particle in the region 2. So in the region 2 is equal to, so not equal to 0, in the region 2 is not equal to 0, not 0, not 0 means the probability of the finding the particle in the region 2 is existing, such type of phenomena we call it as, therefore we need to take the probability in the region 2 is equal to how much probability we are existing, for 2k1 square is divided by modulus of a square, 2k1 square is divided by modulus of a square into k2 into k1 plus ik2 whole square, which is not equal to 0. So therefore what we have to write, the probability of the finding the particle in the region 2 is finite. The probability of the finding the particle in the region 2 is finite. So now you have to take in the region 2 is finite, because it's 2k1 square modulus of so 2k1 square modulus of a square into k2 into k1 plus I k2 whole square is not equal to 0. So therefore the probability of the finding the particle in the region 2 is finite, although the transmission probability is 0. Although transmission probability is 0, so this can be explained by a beautiful quantum mechanical phenomena, that is the barrier tunneling phenomena. So what is the barrier tunneling phenomena? A lesser energy particle can penetrate through the higher energy barrier. So that is the beautiful phenomena. That phenomena we call it as a, which phenomena? Tunneling effect. This is very important effect. Now you have to see here. So then V naught is, so now you have to take that particle energy is E. So therefore some portion of part should be incident, that particle is incident with a e to the power of I k1 into x, some portion of part should be reflected back, b e to the power of minus I k1 x, some portion should be decayed, so that is d e to the power of minus k2 x. This is the exponential function. We are getting that exponential function when what is this? When E is less than V naught. Such type of phenomena, a lesser energy particle can penetrate through the higher energy barrier. So a lesser energy particle can penetrate through the higher energy barrier. A lesser energy particle can penetrate through the higher energy barrier. Such type of phenomena we call it as a tunneling phenomena. This is very excellent phenomena. So this is the quantum mechanical phenomena is overcome the classical mechanics forbidden region. Clear? So this is very important conclusion based on this potential step we are discussing now. Now you have to see how you able to get the questions in your competitive examination. In GATE 2011 there was a question, an electron with energy is E is incident from left on the potential barrier. So the electron is E is incident from the left from the potential barrier. So what is that potential barrier? This is the potential barrier. This potential barrier height is V naught height is there. And electron energy is so that is the electron energy is E. So what we have to write it is this is the electron energy is E. So is left from the potential barrier is given by Vx is equal to, what is that condition? Once you have to see here, that condition is 0 for x is less than 0. So you have to take it as x is equal to 0. You have to consider is when x is less than 0. So that potential is equal to 0. When x is greater than 0, the potential is V naught as shown in the figure. So what is the condition you have to take when E is less than V naught? When E is less than V naught, when V is less than V naught, once you have to take when E is less than V naught, the space part of the wave function, already we discussed the space part of the wave function, how we have to discuss it once you have to see. So now your incident beam is, so your incident beam is A e to the power of I k1x, this is your incident beam. Some portion of part should be reflected back, that reflected beam is B e to the power of minus I k1x, this is the space part is there. Now you have to take here, there is a exponential decay is there, that is d e to the power of minus k2x, this is the exponential part. Now you able to consider is there A they are considering, instead of k they are going to take it as a space part A they are considering. So that A, how we have to write it is, so that space part is, if you have to take, if you consider k2 is equal to A you have to consider, so that is the constant you have to take it as, so that A is equal to, what is this? So square root of 2m into V naught minus E is divided by h cut square. So therefore what is going to happen? E to the power of minus ax exponentially decay. So this is exponentially decay. How it is decay? Exponentially decay you are going to get it. So what is your answer? Your answer is option B is correct, option A is not correct, option C is not correct, option D is not correct, option B is correct option you have to take it is. This is very important one you have to do. So therefore what we have to write, there is a decay wave function is there. So that decay wave function, how we have to represent? E to the power of minus ax. Like this you able to get in your competitive examination. To understand the problem, then only you able to do such type of questions, otherwise you unable to do such type of questions. First you have to practice and practice, then you able to get the perfection. So please share and subscribe our YouTube channel. If you really likes my teaching, you have to inform to your friends and make them as the subscribers of YouTube channel. Not only YouTube channel, you have to buy and purchase our app course, and you have to learn the physics. Like this we will teach in our classes. So you listen and enjoy and learn the subject and get the success story in our physics field. So then after some time you will become as a good physics teachers in your life career. Thank you so much.